Microphone, great. All right. Good morning, everyone. Welcome. So today, spend most of the time on 12.4, and that'll review, along the way, that'll kind of review some of what we've done in the first three sections. I want to spend the last, if time goes how I think it will, maybe the last 20 minutes, 15, 20 minutes talking about 12.5. That should also kind of be a recap of 12.1, 2, and 3, I'm hoping. I will be available for help 3:30 to 4:30 in the dining hall, Ian 4:30 to 5:30, I'm guessing in the botany lab. And I can also, I'm probably stick around until about 11:15 today, but I'll be over in the dining hall because biology comes in here right afterwards. So again, we should try to exit quickly so they can enter. But I'll be in the dining hall after class till 11:15 or so if there's some quick questions.
Do you still have books outside your...
I did, but they've all been claimed.
Okay.
Not in any...
Everyone's being gone.
Okay. So there are four... There was a pile of four. I'm trying to remember who...
I have one. I don't need it anymore. So I have one.
Yep.
It's just because I'm copying the exercise.
Yep.
Just returning to my meeting and I've forgotten what some...
Okay. Yep.
Thank you.
Put it by his door.
I will.
Yep. Yeah, I think Olivia might have one of the surplus ones. Jeremiah had one, and somebody else, I don't know who, has them all. Yeah. Oh, you have them. Okay. Well, there was a pile, and they just kept, every time I checked, there were different numbers. Next week, assuming we get through this stuff today, which I suspect we will, we'll start next week with chapter 13, which is about vectors. And then calculus will begin probably the following week when we get into chapter 14. So I'd like to start again with names, just to help me a little bit and maybe help some of you. So we could do favorite cacti, but I'm not sure everybody's done research for that. So if you don't want to talk about cacti, you should come up with some other category we should share this fine morning. Favorite animal? Is that
Sorry.
I think so. Again, all right. Animal. All right. We're gonna. All right. I think animal. It might be unless there's someone who wants to put another alternative out. I don't. All right. I think that may be solidifying support for animal. So, but you could do fungus if you wanted. So should we? Where do we want to start? Should we start in the? Do you want to start in the back this time?
Hi, I'm Marielle. I like dolphins.
Okay.
I'm Sydney. I like ocelots.
Is it Sydney with a Y or I? Okay. I-T-N-E. Yeah.
I'm Katie. I really like cougars.
I'm Jeremiah. I really like dogs.
Margarita, koalas.
I'm Jack. I really like ibex.
Nadia. Chicos.
Olivia, I have puffins.
Aspen, lemurs.
Evening primrose. Snakes. Heather. I like apples.
Ian? Animals. I don't think about animals.
You could go with fungus.
Yeah, fungi are closer related to animals than plants. Yeah, I'd say Melanelia lichens, the genus Lichens Melanelia.
I'm Corey, and my favorite animal is called the binturong. It's just also known as the bear cat. It's this creature that lives in Indonesia and climbs in trees, and it has a natural musk of buttered popcorn. That's what it smells like all the time.
Have you verified this?
Well, I haven't seen one,
Okay,
but
okay.
Scientific literature does.
Okay. Consistent reports in the literature indicate that. Yeah.
My name is Aura, and I think my favorite animals are sea otters.
My name is Alba and I was going to say otters until Alba said it.
I guess I'll say I like bears. I'm Teresa, and I like armadillos.
I'm Dylan, and I like penguins. I'm Kevin. I like axolotls.
Thanks.
My name's Crystal. I guess I like pandas.
With a PH? Christoph with a PH? Okay, yeah. Not pandas with a PH. I'm bad at spelling, but I'm not that bad usually. So.
My name is Shinyao. I like giraffes.
My name is Will, and I like salamanders.
Nice.
My name's Tarzan. I like chitons.
Oh, nice. My name's Dave. I like cats. It's kind of sort of had to. Yeah, I know. Predictable, but had to.
What type of cat?
House cats. I mean, I like all cats. There are very few animals I dislike. I think snakes snakes too close are a little problematic. But at a distance or separated with a pane of glass, it's totally fine. All right. So 12.4, that's the main topic for today, is about planes. So we're going to learn all about planes today. And but first, as we often do, let's journey back to the land of one-dimensional functions and think about lines in 1D. And in particular, even why we would think about lines. So here is Calc 1 in a nutshell. So Calc 1 is about rates of change. And somebody said to you at the beginning of Calc 1, what's the slope of this? And you would say, that's crazy. That's a curve. Lines have slopes. Curves don't have slopes. But then you realize, oh, wait, if I zoom in really close, you can try this on your own paper if you want. You say, hey, wait, and then it looks like a line. And I know what to do with lines. I just calculate their slope. So the point is, if you zoom in on a line, on a curve, it starts to look like a straight line, and you can calculate its slope. It's that's all there is to Calc 1. Calc 1 is just exploring the consequences of that observation. And so the zooming in process is a limit. The slope is a difference quotient. And then you decide that that's a tedious process, so people invent shortcuts like the power rule and chain rule and product rule and so on. So anyway, so that's all of Calc 1. And so it all depends on the slope of a line. So we'll do a similar thing for surfaces. So if you have a surface and somebody says, what's the slope of that surface? You'll say, well, what do you mean? That's it's a curvy thing. It doesn't have a slope. But if you zoom in on a surface, it looks like a plane, right? Something that's flat. So if you zoom in on a curve, it looks like a line. If you zoom in on a surface, it looks like a plane. And so we'll do calculus. We'll analyze surfaces by thinking about the tangent planes. Here we do calculus in 1D by thinking about tangent lines. So planes are going to be super important. There's an exception to this, I guess, if you have, all right, so just to contrast. So this bendy thing looks straight, if you get close enough, but a pointy thing does not. So there's a little bit of mathematical fine print. It's the same thing like a surface. So a curved surface, if you zoom in really close, right, that starts to look like a plane. A pointed surface, this one's a little dangerous, so be careful doing this one. If you zoom in on a point, that actually doesn't start to look like a plane. Again, you want to be a little careful if you try that one. All right, so the point of all this is that planes are going to be really important for two-dimensional calculus. So we need to think about how to describe planes, just like in order to do 1D calculus, we need to think about how to describe lines. So let me just say a few things, and then we'll start this with a quick little exercise. So what makes a line a line? Sorry, that was sort of an oddly existential question.
Continuity.
It's continuous, and its slope is continuous. So what would make a plane? Sorry, its slope is constant. Its slope is continuous, but the slope is also constant. It's the same slope everywhere. Slope does not change. So what would you think would make a plane a plane? Same slope everywhere. But now you have different slopes because it's a plane. It's tilted in space. OK. So now I think you know all you need to know about planes to start figuring things out. So let's get things started with what I think will be a pretty quick exercise. Let's do problem 1, and maybe we'll get to problem 2, and then I'll write some formulas on the board. All right, so let me say a few things about problem 1, which was designed to sort of provoke a certain to lead, and provoke is the wrong word. Lead us to a key equation. So, what are some ways to think about this? So I know we want to know what happens when I get to 3, 5. So if we start at the origin, we start at 7. And then if I go to x equals 3, I've moved 3 in the x direction. And I know I go up minus 3, i.e. down 3, for every step I take in the x direction. So then I would say, all right, so let's see, maybe this, right? Minus 3 times 3. So I've lost 9 in doing that motion. And then I need to go from y equals 0 to y equals 5. And I gain 2 for every y step I take. Do people see where this is coming from? Got oddly quiet for a second. All right, so let's see. We can. This is 14 minus 9, so that's 5. Is that right? 8, 14 minus 8. OK, all right, yeah. I don't like subtraction. OK, so do the sort of the numerics of this. Some okay, folks. Subtract my subtraction challenges aside. So now the question is, what is the equation of this plane? So you've almost written it out here. So so this was how far you have to go in the x. Like if I said, what if now it's 13 and 25? You would just do the same thing. Like, OK, I'm going to start at 7. I'm going to take 13 x steps. 13 is minus 3. I'm going to take 25 y steps, and I'm just going to see what I get. So this, what I'm trying to suggest is that this formula, oops, that's a minus. Which is probably not a shocking result. I mean, it sure looks right. So the point is, like, planes are two-dimensional lines, constant slopes. And we know, right, I guess I'll do that over here, right? Y equals mx plus b. So now it's just we've got an mx and we've got an ny term or something. So the general form for the equation of a plane it seems to be conventional to use c instead of b. But you can keep using b if you want to, if you long for the days of 1D calc. So basically, you've got two slopes. They're constant in each direction. If you're given a point on the plane, so here it was nice because like I told you what the z-intercept was. But if I had told you instead the altitude, the z value at a different point, say x naught, y naught, z naught, then you would have, let me make sure that I write this right. So this is a plane with slopes mn. I don't want to say this. With z equals c at x naught, y naught. So that's sort of like the point slope equation, but for a plane. So anyway, these are going to be useful equations. We'll be working with these sorts of equations a lot, and it's really the natural analog of what you would have in one dimension. Yeah.
Can you explain the two slopes? Can you get? I mean, it's a plane. How will it have two slopes?
Let's see. Okay, so here's a plane. And if I go, let's say, between you and me is the x direction. And so then that would be a negative slope. I'm going downhill. On the other hand, if I decide to make a run for it out that door, and I'm going this way, my slope happens to be 0. So basically, a slope is how much do you rise if you take a step in a certain direction. So like if I'm here and I want to know what's the slope this way, I would take a step this way and then see like what happened. Do I go up or down? And then I would say, what's the slope this way? Well, I would take a step this way and see what happens. Do I go up or down? Exactly. Yep. Yep. Yeah.
So does that necessarily have to be in one of like the cardinal directions, or can you do that for pretty much any direction?
You could do it in any direction. You could say, all right, you're skiing and you don't have really good techniques. You don't want to ski right down because you might die. It's too steep. It's going to have to go with this death and skiing metaphor. Why not? So you decide, all right, but if I go at an angle, that'll be okay. So then you could say, all right, so what's the slope here if you take a step in this direction? And so that general idea is called a directional derivative. And what we'll need some vector machinery in order to figure out how to calculate that. So that's sort of where Chapter 13 will give us vectors in our toolbox. And then we can put it all together and come up with some really nice machinery that'll let us calculate the slope in arbitrary directions at any point. OK, so let's explore planes a little bit more. So let's try problem 2, which I know some of you have tried, and then problem 3. I'm not convinced we're going to do problem 4, but so I'd say, but anyway, so yeah, give problems 2 and 3 a try using these ideas, and we'll see what happens. All right, so let's spend a little bit of time going through this example. So first, problem 2, the table of numbers. The thing to note is, I didn't reproduce the entire thing. Right, what makes a plane flat? What makes a plane is that the slope is constant. So that means every time you take a step in this direction, you're going up 30. It's the same amount. And every time you take a step in this direction, you're going down 24. So if you have a graph, a way to tell if it's a plane is if it's flat. This is not super profound. And if you have a table of numbers, a way to tell if it's flat is that it's the same increase in altitude or whatever for each step in every time. But note that the increment here, the x slope, is different than the y slope. OK, so the next one, we're given a function. It's a plane. You can tell it's a linear function. It's of the form that I just had over on that board. And so you can fill out a table of values, which I didn't repeat on the board. But let's jump to thinking about contour lines. So a contour line, it can be helpful, particularly if this idea is still a little uncomfortable, is to just sort of like remind yourself what a contour line is. So you're asking, like, all right, what are all the x, y values for which z equals 0? And this is arbitrary. I don't know. It seems like 0 is a nice number to start with because it's pretty easy to work with mathematically. You could decide to do a contour line for the altitude value of pi or 613 or something, but 0 isn't often a nice choice. So then, all right, well, I have this question. Who's going to answer it for me? Well, the equation. That's the only information we have. So I just plug 0 in for z, and then I say, all right, well, what do I get? So at this point, once you plug in z equals 0, you now have a one-dimensional situation. It's just a line. Y equals mx plus b. I did a little bit of algebra, boom. And y equals mx plus b. I plotted that here. So this is my z equals 0 contour line. Slope with a slope of half, intercept of 2. So then we say that was fun. Let's do it again. All right, so now we need another contour line. What are the xy values for which z equals 1? So then who's going to answer that question? Well, the equation. So I plug in z is 1. Now z is gone. It's a one-dimensional function, just x and y. And I get this. Slope is the same. And that's sort of kind of maybe feels right, because slopes are the same in these planes. Different intercept. Intercept is a little bit lower. So I drew this. I'm not quite sure what's happening to my scale here, but we'll let that slide. So z of 1 is here. So at this point, you don't need to keep playing this game, because you can kind of see what's going to happen. That you're always going to get this half x, and you're just going to get different values for the intercept. We know that this is a plane, and planes have constant slopes in all directions. So we would expect the contour lines for a plane to be parallel lines. And that's indeed what we see here. And so if we kept going, again, this is taking even more artistic license. 2, 3, minus 1. But it gives the right idea. So now we can begin to picture this. So this is going to look something like this. And maybe you know how to draw that. I'm pretty sure I don't know how to draw that. We could see how Wolfram Alpha draws it, but I thought it wasn't worth making the screen come down and darkening the room, looking at a plane and saying, yeah, it's flat, and then turning the lights back on and shocking you all. But anyway, you can always dial up Wolfram Alpha on your own to do that experience. All right. Questions so far? We're doing all right? OK. So let's see. So then what else was I asking? F of 4 and y. So this means we're going to stick x at a constant value of 4 and then see how z varies as y varies. So I just plug in for x equals 4. 4 plus 4 is 8. So I get this line 8 minus 2y. That's an intercept of 8, a slope downward of negative 2. So let's see. So this says, right, so this is a slice of this surface, this plane. This says that as y increases, the altitude decreases by 2 every step. And it starts at 8 at the OK, so this point here is the point y equals 0, x equals 4, because we fixed x equals 4 here. So it would have been helpful if I had drawn those next to each other, but so x is 4. That's somewhere out here. I'll be at an altitude of 8. And then if I go in the y direction, I'm going downhill. Does that? Where did I put my plane? Oh, here it is. All right, so we're kind of here. We're at x equals 4, y equals 0. If I move in the positive y direction, that's up. I'm going downhill pretty steeply. Okay. So this is, now I'm going to fix y at 4 and say what happens to the altitude as I move in the x direction. So again, I just plug in y equals 4. I do the math, I get x minus 4. So this tells me I'm going to have an intercept of minus 4 with a slope of 1. I'm going up in the x direction. Slope in the x direction is 1. Slope in the y direction is minus 2. So let's see if we can see that over here. Let's see. So this is now, what did I do? I set y equal to 4. So it does indeed look like I have no idea what I've done with the scale on this, but when y is 4, the altitude is indeed negative, right? Because I've had like a minus 1 contour here. And then this says if I move in the x direction, I'm going up. And you can see that that's the case. You're going higher in terms of the contour lines, or if you were sort of to draw this, and you're moving in this direction, you're going up. You're getting closer to you. Is this holding together all right? OK. Let's see. So then the last question is, suppose you're at the origin. What direction? Let's see. So if you're at the origin, first, what's your altitude? Your altitude is 4. So clearly, I've messed up the scale on that, but hopefully, I can get a little bit of artistic license. So you're at 4. What direction? The directions here should be OK. What direction would you have to go in order to maintain your altitude of 4? You walk on the contour line. Yep. So that would be, whatever that direction is. We haven't really talked about directions yet. You could, well, what do we know? We know this. Oh boy, let's see. It would be that, right? Because this is a slope of a half. So you rise 1 when you run 2. So whatever this is, pi 8 sounds pretty plausible. So that's sort of the basic idea. What if you wanted to go downhill as fast as possible because you're feeling good about your skiing techniques? Yeah, you would go right directly in that direction. Yep. So it would be perpendicular, right? So and you sort of know this from maybe navigating Cadillac Mountain or looking at contour lines, right? If you go along a contour line, you're staying put. If you want to challenge yourself and go up Cadillac the most steep way possible, you go from one contour line and you go as fast as you can to the next contour line. So I was going perpendicular. We'll learn in the next chapter how to describe these directions using vectors a little bit more formally. So I was in this one I was looking for any sort of answer, an angle or just a direction or even pointing. Questions on this example? So again, the key, this has been the case also for all this chapter. The algebra of this is not any more difficult or easy than the algebra from 1D. But now you've just got 2 things to keep track of. And very often, well, I don't want to keep track of 2 things at once. So we'll just do one thing at a time. What's the y variation? What's the x variation? Or what's the x slope? What's the y slope? You can kind of get rid of z altogether and just say, I just want to know what the level set looks like. Where's my z equals 0? Where's sea level on this surface? Where is 1 foot above sea level on the surface? Yes? OK. All right, go ahead.
Sorry. So for a function, you can have an x and a y slope that doesn't change, but the function itself.
Yeah, so your altitude changes, but your slope is constant. Just like in 1D. So the slope is constant, but the function is getting larger all the time. And so in 2D, you can have constant slopes, but your altitude is changing all the time. Yeah.
So that'll give the visual of a steeper slope in some parts.
Yeah, if you had something like the paraboloid, the bowl-like thing I've been working with, there the slope is getting steeper all the time, although all the slopes are getting steeper. Yeah. But I think the main thing, I'm stumbling a little bit because we haven't really talked about how to talk about slopes for surfaces, because there's not just one slope, there are multiple slopes. That's part of why it doesn't map onto 1D exactly. But I think the main takeaway from this is that for a plane, the slope is constant in whichever direction you walk. So whatever, if you're on just for a plane, that has constant slope, yeah. And that's what makes a plane flat. Its slopes doesn't change. Yeah.
So behind you, the two equations at the 4, y.
Yep.
So when you take those two resulting equations from those and kind of put them together, you get that equation up there. Is that just coincidental, or is that something we can do, if we're looking for stuff? I just feel like there's no way, if you add x minus 4 and 8 minus 2y, you're going to get the equation up there that we started with, 4 plus x minus 2y. So is that some way we can analyze planes, or is there any use to that, or is that just some random thing that I did that doesn't really matter?
That's a great question. Let me think about it. So this is, it certainly wouldn't be the case if I had done sort of different numbers here.
Yeah.
But I think it is, basically, it may not always be as simple as directly adding, but certainly it's the case that these two bits of information together tell you what the plane is. Because I'm telling you what the value is at a particular point, and you can here's, I guess, another way to say this. If you look at this, you say, OK, it's a plane. I know the y slope. It's a plane. I know the x slope. Now, all I need to do is know one other point, and I figured out the plane exactly. All I need to know is where does it start, where does it end, and you can just figure out any of the intercepts from this sort of information. So certainly, you can go from f equals x, y to this, and you can certainly go from this and this back to that. Yep. Yep.
I think it works
Yep.
so nicely because the numbers you use, if you plug them into the original equation, you get z of 0. And so
Right.
It's kind of like this middle point that I think if you use another thing, then you'd have to account for that when we were looking for other points.
Exactly. Yeah. Yeah. Yep. Yes.
Since this is all perpendicular to the z-axis, would it be possible and or correct to just pick any arbitrary line along there to call to put as, in that example, to put as the horizontal axis against the z-axis? So would you be able to put, would you put the perpendicular line to that? Would you put negative y minus 2x along there to map that line as the horizontal axis to z?
I'm not. Do you mean how would I put if I wanted to take this from a 2D graph to a 3D graph, where would I put the y-axis?
If you wanted taking any line along that we put in the contour map and making that the horizontal axis. Since it's all perpendicular.
Yeah, I think you could. You're always free to change coordinate systems. So you could decide to come up. Maybe what you're saying is, all right, these axes are nice, but I want to use these. So yeah, you could, and then in this different coordinate system, the plane would have a particularly nice formula. And what would that be? That would be this is a half, so that's how far do I have to step in this direction? So we figure out what m would be. So you can always rotate coordinate systems. I don't think we'll typically do that in this class.
Would you be able to like express the coordinate plane with the horizontal axis being defined by two variables though?
Yes, and that is what linear algebra is about, which is a class you would take. Another sort of one of the standard post-calculus classes. It's sort of how do you do these linear coordinate transformations. So yeah, so I don't think we'll do much of that in this class, but it is certainly worth noting that just in general, and this is certainly true for more complicated open-ended problems, sometimes a choice of coordinate system you're handed is not really the best one. So you can sometimes make your life a lot easier by defining the x-axis in some convenient fashion. That happens in physics all the time. Right, so somebody gives you something along a diagonal, and you say, all right, well, that diagonal is now my x-axis. Nobody can stop me because coordinates are arbitrary. OK, so what I want to do for the remainder of the time, and this might be 15 or 20 minutes. I'm not sure. So I'm going to guess this is going to be about 20 minutes. We'll end a few minutes early, which is so people can ask homework help if people want, I think, but I'm not exactly sure how long this is going to take. So I want to spend some time talking about functions of 3 variables. So just when you're starting to feel comfortable about 2-dimensional functions, let's really blow our mind and think about arbitrary dimensional functions just for a minute. And then I want to draw some graphs that I think maybe will help tie some stuff together. So let's see. I guess I'll work over here. All right. So OK, so one-dimensional calculus in the days of yore, one-dimensional functions. One input, one output. You tell me x, the function tells us y. We spent this week thinking about these sorts of things. So now there's an x and a y, and we need to and the function tells us what z is. And that could be, we often think of that as an altitude, sort of how we visualize it. But it doesn't have to be an altitude. This could be, this could be your profit if you sell x ice cream cones and y cookies or something at your store. But we visualize it as a surface. We could also have something w equals f of x, y, and z. And so this would be a function of 3 variables. And here the idea is that for every point in space, the function has a value. These are very difficult to picture, maybe impossible. But I like to think of these in terms of temperature. So here's we are enjoying this calculus class in a 3-dimensional room. And every point in the room, there's a temperature. And as you maybe don't notice, but I notice when I walk up and down the stairs, it's a lot hotter at the top than at the bottom. Sometimes, and maybe I don't know, people sort themselves out in a class. Some people like to be up front. Some people feel more comfortable in the back. But there's also like thermodynamic implications in this classroom, because the back row can get really warm, and this row down here can get a little chilly. Anyway, the point is, at every point in space, there's a temperature. It's sort of hard to picture that, but it's maybe not so difficult to imagine that. We could also think maybe in terms of a concentration. There's a carbon dioxide concentration at every point in the room. Hopefully not much, but see. Could also, again, it doesn't have to be spatial. This could be the amount of profit you make if you sell this much ice cream and this many cookies and this many, I don't know, servings of kale at the COA cafe. Yeah.
So when we're talking about like which dimension each of these are in, like is it by how many like inputs and outputs you get?
Yeah. So and that's partly where this is headed. So I would say, wow, that pink erased well. Usually the pink sticks around for longer. All right, let's see here. So we'll we're going to look at like 1, 2, and 3-dimensional parabolas. So okay, so in answer to Katie's question, I would say this is a 1-dimensional function. And what do I mean by that? Well, there's only one input, x. The result is a line. Lines are 1-dimensional. But note, the line does curve through a 2-dimensional plane. Let's see. So I'm going to put a graph here in a moment, so just in case you're trying to like preserve space in your notes or something. OK, so now let's think about a 2-dimensional parabola or paraboloid. Oh boy. OK. So this is z equals x squared plus y squared. So this is a bowl, right? We're seeing pictures of these. This is an example from the first day in class. So this is a 2-dimensional function. Why? Because there are 2 inputs, x and y. The resulting mathematical object is a surface. So this is hollow. It's not solid. But it's a surface that bends through 3-dimensional space. Just like this is a line, a 1D thing that bends through a plane that's 2-dimensional. So let's think about contour lines and level sets, which are the same thing. So the contour lines here, we've seen that they're circles. OK, thank you. Somebody's nodding, which either means you know you're supposed to nod or you're remembering. In either case, it's oddly reassuring. OK, so contour lines are right. So contour lines, you would set like c equals x squared plus y squared. And I think we did this the first day of class, second day of class. And we said, oh, hey, those look like circles. And all right, that's, again, scales off a little bit, but so I roll with it. And so the contours are getting closer together because it's getting steeper. And notice what happened here. We've got 3 variables. We fixed z at a constant value. And now the contour line, the level set, is now a 1-dimensional curve on a plane. So we're kind of like you go down a dimension when you do a contour line or a level set. Let's think about level sets for this function, which would be kind of a weird thing to do, but it's good to, it will be a useful maybe thinking exercise. We'll see. So suppose, right, so when we're doing contour lines or level sets, we want to say, what are all the xy values for which z is a particular value of c, 0 or 2 or 3? Here we might want to say, suppose we want to know the level set, the contour line for 1. What are all the x values for which y equals 1? 1 and -1, yeah. So these 2 dots are the level set for the z, or like the z equals 0 contour line or level set for this. And you could imagine, right? I mean, you just say like if I had a knife that could cut through the blackboard, I'm almost picturing like those like when you have some clay and you can like slice it with wire. So I'm sort of imagining doing that. So like if I had this shape made out of clay, and somebody had spent a long time making a nice little bit of pottery over in the pottery studio, and before it was fired, I came by and said, "Excuse me, we need to do math," and I sliced it. Just to make it a little more vivid, right? So if you take this bowl, this like paraboloid thing, and you slice it, it looks like a circle. Yeah.
So for the one-dimensional example, there's really no notion of like continuity at that level.
Right, and that's why sort of the general idea of these are called level sets, and because a set doesn't have to be continuous; it's just a collection of points. So, and then we could do, what are the? So this would be like the y=1 level sets. If I wanted to do y=2, that would be plus or minus square root 2. So this would be closer still. It might be easier to sort of think of over here. So like first I slice it at 1, and I get these 2 points. Then I slice it at 2, I get those 2 points. Then I slice it at 3, I get those 2 points. And because it's getting steeper, each slice, the little points I get are closer together. So here, so what am I trying to say? So we have some mathematical object. When we do the level set thing, we're going down a dimension because we're slicing it. We're slicing it in whatever we're thinking of as vertical. So a slice of a 3D object gives you something that's 2D. A slice of a 1D object gives you something that's 0-dimensional points. Yeah?
This might be a little bit of a stupid question, but I've been really confused when we've been saying, calling like the object over there that you just said was 2-dimensional, but when we've been calling it 2-dimensional, because isn't it 3-dimensional? Because it's like got 3 directions to it? I don't know.
Yeah, no, that's not a stupid question at all.
Okay.
So it's a 2-dimensional object that lives in 3-dimensional space, which I'm aware doesn't. I was just letting. That's not the end of my answer. I just wanted to like pause and let that sink in for a moment. So what I mean by that is suppose I wanted to get you to some point on this bowl. And you would say, OK, you're going to have to tell me my x, y, and z coordinates, because you're rightly pointing out, well, this is in a 3-dimensional space. But I'm saying, actually, because of this relationship, I really only need to tell you 2. Okay. Because once I tell you 2, you know what your third one is. That's what the function tells you.
So if we were like working with a sphere, for instance,
yep.
would that change things?
Not really.
You can take any formula, basically, rearrange it in terms of this, so rearrange through z, and then since you have that value, you can find it, even though it's in 3-dimensional space, you only have to use 2 dimensions to find it.
Exactly, yep.
Okay.
And that's exactly what this, in the general case, says. Like, there's x, y, and z, but we're going to restrict ourselves to this relationship, so actually we're now in a 2-dimensional thing instead of 3-dimensional. Yep. And same thing here. Like, you might think, hey, you need 2 coordinates, an x and a y. And I say, no, actually, once I tell you x, you know what y is. OK, so now let's attempt to think about these. So suppose now we have w squared equals x squared plus y squared plus n squared. OK, so now this means at every point in space, there's a temperature. So that's, sometimes I like to, you can also think of this like in terms of a concentration. And so I sort of like imagine like ink dots in space or like a fog. And so like the larger the value, that should be just w. The larger the value of w, the denser the fog is there. And so at least I can sort of picture that. You can't really picture that because the fog obscures things, so you can't see sort of on the other side. But at least it kind of gives one something to think about. If you've seen some of the confusing drawings of electron orbitals, they're confusing because they're trying to show you a density, in this case a density of probability, in 3-dimensional space. So it's confusing because what in the world is the density of probability, but it's also just confusing geometrically because you're trying to show this three-dimensional function. So in fact, so just like this is a two-dimensional object in three-dimensional space, this is a three-dimensional object in four-dimensional space. So again, it gets like sort of undrawable. But if you think about temperature, it's not so strange. But you can think about the level sets for three-dimensional functions. So we could ask, what's the set of all points that has a constant temperature? And that would be, and that's going to be a surface. So like level sets. Level sets. So if I wanted suppose I want the W equals 100 level set. So I want to know, so maybe the heater's on full blast and the thermostat's broken, the opposite of the problem that Ian House have. Probably like on average, we do home heating really well in Maine. It's just that like half the houses are overheated and half of them are underheated. Or at least that's how I feel about the campus. In this room, there's probably like right in the middle row, where Heather and Evening Primrose and folks are, like that. Maybe that's like the optimum place in this room. Anyway, there is a pretty strong, well chosen. Anyway, there's a pretty strong temperature gradient here. So anyway, so suppose like there's a part of the room that got up to 100. I could say, well, show me all the points in the room that the temperature is 100. And so the point is, if it was described by this weird function, that would be which I mean it's not, but let's just pretend because it's simpler. This is the equation of a sphere. So the level sets in this case, and then if I wanted to know, all right, what if I wanted to know, like, where is it 64 x squared? Then I would set and so the level sets are concentric spheres here. So the picture might be like layers in an onion. Again, it's really hard to draw because once you draw one, you've covered up the one you just drew that was smaller. So like there's a figure in your book that sort of shows what these concentric spheres might look like with a sort of cutout so you can kind of look in them. So the visualization for this gets harder and harder and harder. And of course, there's no reason why one has to stop at three-dimensional surfaces and four-dimensional spaces. If you're doing big like macroeconomic models, you should probably stop because they're not really true. But if you, sorry, but anyway, if you decide not to stop, right, you might have like what's going to determine the jobs? Like there's a big jobs report today. What's going to determine the jobs report in January? Well, your model might have like 12 or 13 different things in it. Right, and so then you might, so maybe jobs report is like what you're trying to figure out, and then you might have 13 things over here. So once you get above this, you just stop trying to draw. But it's always useful to kind of go back to these pictures. So when mathematicians say things like, oh, well, it's a 13-dimensional surface in a 14-dimensional space, we can't picture it, but we're just sort of like thinking as if it was 2 and 3. So we'll do a little bit of stuff with three-dimensional functions, because they come up in science all the time, right? Like electric fields, magnetic fields, gravitational fields, potentials, temperature, concentration, orbitals, and so on. So the book will do a little bit with this. So we're not going to try to visualize it too much. We'll focus mainly on this stuff. So I might assign like one or two little sort of visual problems from 12.5. That's what we just covered. And then that sort of brings us to the end of chapter 12. So what we'll start with next week is a bunch of vectors. We're going to need to have like really good, well-oiled vectors in our toolbox, because as we've seen, slopes depend on direction. We have to talk about direction. Direction is what vectors give us. So we'll do a bunch of stuff with vectors next week. And then at the end of next week or the beginning of the following week, we'll start doing multivariable differential calculus. So I will pack up and be over in the dining hall if people have questions.